Okay, so first of all, thanks for having me and letting me present this today. So as you can see, I will talk to you a bit about Exascale Hydrodynamics, specialized for astrophysics using SYCL, and especially using the Shamrock framework that I started developing during my PhD, and I'm continuing to work on it for my postdoc now in Grenoble. So first off, let's start with some computational fluid dynamics. So one of the main important fact when we work in astrophysics is that we have an insane range of scales and also of densities. For example, if you are looking, for example, at the Milky Way and want to simulate the formation of star or even planets and obtain like protoplanetary disks like this, you will need to resolve about 10 orders of magnitude in scale. Since this is very large, you will need a lot of precision and the need for double precision floating point arithmetics everywhere. On the other side, compared to the normal world where you will have like kind of standard physics, in astrophysics, we have many effects. So they range from non-local effects, typically gravity, or magnetized flows, the presence of dust tracers, presence of planets, and so on. The physics can be very diverse, and as such, for maintainability, we need to use the DAG base scheduler of SYCL. I will touch a bit on that later. So now that we have some hydrodynamics, there are multiple ways of actually performing such simulation. On one side, you have finite element methods, where you will have just a discretization of your simulation and discretize also the differential operator, and you will get a simple scheme in general, which tend to be also the fastest kind of scheme for hydrodynamics. Now, if you want to resolve typically shocks accurately, you will need to move to another method, as finite elements are not that great for that. Typically, you will look at finite volume method, typically the Godunov scheme, to properly resolve shocks. However, while it's one of the most versatile schemes, you may want to use something that doesn't even have a mesh. For example, in the disk I showed in the beginning, some disk in astrophysics can be completely warp twisted. You can think as a twisted pancake kind of geometry. And to simulate such geometry, having a mesh is an issue because the flow is very misaligned with the grid. And you will need to use meshless method, typically SPH, where instead we completely trade off performance for such the ability to resolve weird geometry. Typically, we can think of 60 neighbors per particle, which is quite low. Anyway, it's quite hard to implement all of them in a given framework unless you realize something. Basically, all of those schemes are about the same, in the sense that in all of those schemes, you have neighbors that are defined by an interaction criterion that will just tell you whether two objects in the simulation will actually have an effect on each other. And the actual numerical scheme that will tell you how to update any given element as a function of its neighbors. As such, if you can manage to abstract away those two elements in a given framework, you can code, in principle, any given scheme. And that's what we are trying to do in Shamrock, is having a framework where ideally we can specify just a criterion and such a scheme to get a numerical method with exascale scalability. Also, this means that we can have generic modules that we could apply to any methods in the code, allowing us to only code generic modules, typically chemistry or those kind of things, once and use it in all of those schemes. Also, having such a framework allows us to have to optimize all the schemes at the same time. So that's basically the global picture. It's a C++17 templated framework that is targeting multi-GPUs using both SYCL and MPI. I will touch on a bit on this later. We are interoperable with Python in the sense that basically to use the code, you are just calling Python to say, well, add the disks there, do a simulate until that, and so on. It's much simpler to us. Basically, we are doing runtime switch a bit everywhere in the code. We have only one way to produce the code beside backend if-defs. Basically, there is one code with everything compiled in it. And we have, as I say, multiple hydrodynamical solvers. So now, exascale supercomputers. As you may notice, since a few years now, if you look at the largest 500 supercomputers in the world, they are all using GPUs now. Even worse than this, they are using GPUs from all the different vendors, which is a bit of a pain. But also, on the other side, we can see that lately a lot of supercomputers are getting like just disconnected and replaced by more modern counterparts that do involve also GPUs. So if we want to follow that trend, we basically have to migrate toward GPUs and also use those large clusters. To do that, we had many choices. So most of them were some possibilities, but we choose to not use those because of either lack of support or performance, or because they are proprietary, or because it will be just way too hard to maintain for a large code base. As such, only two real contenders were up to us, either SYCL or Cocos, and we chose to use SYCL as it's an open standard. We'll see also, because I'm very interested in the DAG-based scheduling, it's a very good thing for us. And but SYCL has a very low adoption in astrophysics. In my part of astrophysics, I'm basically the only one. So that was not an easy choice. Anyway, so for the DAG-based scheduling, in SYCL, there are two ways of scheduling kernels, either using in-ordered queues, you can think them as CUDA streams, or the DAG scheduler, where we will just schedule kernel, say basically which kernel depend on which dependencies from the other kernel, and the scheduling will be somewhat automatic. In our case, since we have many hydrodynamical solvers as well as multiple effects that can be toggled on and off, there are way too many control flow possible in the code for us to feasibly build up something using in-order queues. So just for maintenance, we are basically forced to use out-of-order queues. Also, because of that, we choose to initially use SYCL buffers, but they have a few issues. SYCL buffers typically have no interoperability with USM in a standard way, that is. And you will need USM pointers to actually use MPI, BLAS, FFT, you name it. Also, they like finer memory control. They add an additional latency, as it will show with SYCL Bench 2020. And also, USM in general allow for more optimization. So we are slowly doing that migration now. But while keeping out-of-order queues, we are trying to minimize refactoring using like thin wrappers on top of USM nowadays. Anyway, that's about SYCL. For the framework itself, basically everything looks a bit like this. On one side, we have the domain decomposition, then the tree algorithm that we will use to find the neighbors, and then the actual physics update. First off, with the domain decomposition. So you take your particles in a nice astrophysical simulation, nice box, and you will subdivide that box into subdomains that we call in the code patches. Each of those patches can either split or merge. Typically, if some particles start to concentrate in a given patch, we'll just split it in order to have, in average, the same amount of particles in each patch. Then, once we have our patch, we will just schedule them on the GPU. So just looking for that. In order to do such a scheduling, we need to do a bit of load balancing. And to do that, we take each of our patches, and each of those patches will take a certain amount of time to be updated. What we do in Shamrock is that we'll just have this quantity W, that is an estimated load, that is, in principle, should reproduce or be proportional to the time it takes to update a patch. And according to that load, we can actually do the load balancing in such a way that the sum of the load will be the same in every GPUs. So this means that if you have a perfect load model here, and you have enough patches, in principle, your load balancing should be optimal. Now you need to communicate between the domains also. So if you take a blue particle here, the neighbor of that blue particle could be very well in another GPU here if it was the green particle. As such, you need basically that GPU need to have access to the data that is here. Just doing a kind of remote access thing will be too costly. So instead, we just mirror part of each patches to the other. So for example, patch 1 will send part of its data to patch 0. And that's what we call ghost zones. To actually do the communication, there is quite an advantage with SYCL, is that since we are using just pointers, we can use standard MPI. So here, for example, you have a node from the Lumis supercomputer. On that node, you have the CPU part that is here, and here all the GCDs that you can think of as the GPUs. Everything is basically interconnected using quite fast pipe. And more importantly, you have actual network cards that are directly attached to the GPUs. And in order to use that, in MPI, basically, normally, you will have a pointer that points to your device and be able to perform actual MPI call on that pointer that point to actual device memory. Thankfully, in SYCL, since malloc device just return, for example, a standard CUDA pointer or standard pointer for ROCm, level 0, whatever, you will just be able to call MPI send, MPI receive as usual, and it will just work, and you can do direct GPU communications, which gives you much better latency and bandwidth. Anyway, to perform the actual communication in Shamrock, we are using sparse communication. As we've seen previously, for the go zone, like every patch has to send some data to the neighboring patch in the simulation. Of course, this thing is quite sparse. Not every patch has to send data to every other patches. And this is, for example, an example of a communication matrix that we have in the code. So the first step to us will be to pack message together into messages that are between a pair of ranks. So every patch will send a message to another patch. We'll group those messages into any rank, MPI rank, we want to send the message to another MPI rank, and then perform the sparse communication on those messages by just basically collecting the global list of communication to perform and perform non-blocking MPI communications. Anyway, so this is the MPI part, the domain decomposition as an org tree of subdomains. And now, in every part of the simulation, now that we have the data and that we have the neighbors in the correct GPU, we need to be able to find the neighbors. And that's where radix trees come in. So now you want to look for neighbors. When you want to look for neighbors, many ways, you have many ways of doing so. One of such way is to use an actual tree algorithm to search for your neighbors. You have two ways of constructing such trees. One is just to use whatever tree construction and just update it as the simulation evolves. But this is a bit too slow, especially if you have domain decomposition operation, you will have to basically update everything. So instead, we choose to not bother with such issue and just use on-the-fly parallelized tree building algorithm to just rebuild the tree whenever we need it. The idea being that we don't want to communicate any trees. We just discard them at the end of the time step and rebuild them whenever we need to. To do so, we take a particle and map them onto a fractal curve. And we use the list here of Morton codes because they are a Morton curve, and use a parallelized tree building algorithm developed by Tero Karas at NVIDIA in 2012. But if we are only limiting the procedure to that, we'll have some issue. First off, you can have only one particle per leaf of the tree. But as I said, in SPH, you have about 60 neighbors. So that means that your neighbors will be spread out across 60 leaves. That will be a bit too costly for performance. So we want instead something like 10 particles per leaf, which is in general the optimal in performance. And also the Karas algorithm cannot duplicate in the Morton code. And since to get from the actual position in the subdomain to a Morton curve, you are doing a conversion to an integer, you could have conflicts. So instead, we are using a reduction algorithm that exploits the binary arithmetics of Morton codes to remove duplicate and reduce the number of leaves before the actual tree building. It looks something like this. We are, so first off, as usual, converting the position to the position on the Morton curve. Then we sort the Morton codes, do multiple paths of reduction until we get the code that will generate the tree with some missing leaves, and then do the parallelized tree building. And once we have the tree, we can do a first neighbor search where each leaf of the tree will look for neighbor leaves and use that result to actually find the neighbors with our particle. So it's a search in 2 stages. Then in terms of performance, if we benchmark the actual tree building part, we see that we get about 200 million particles treated per second in the tree building step. This equates to about 5% of SPH time step, and as a result is sufficiently cheap for us to just rebuild the tree whenever we need to. But This could be very well optimized by first reducing the allocation latency, which correspond to that line here, and also increase the performance of the sorting algorithm. Here we are just using a very crude implementation of a Bitonic sort. This could be totally replaced by some algorithmic libraries in some implementations. Anyway, and for the tree traversal part, here we are also, so it's the two-stage of search I spoke about. So first off, if we don't use any reduction, only the removal of duplicate codes, we'll get about 10 million particles per second for the neighbor search. Now, if we start to apply some reduction to the tree, we can bump this number by about a factor 10, if we use the level 5 or something like that in reduction, to about 100 million particles per second for the neighbor search. But here we could exploit very well ray tracing units. Basically, this is AABB intersections within red X trees, which is basically ray tracing. And we also could have better memory access pattern and task balancing and scheduling to bump up that performance even higher. Anyway, now in terms of performance of the global code, we want to compare against a reference code, that is the Phantom SPH code, that has been used for about 15 years now in the astrophysics community, especially the community of protoplanetary disks. But this code has no great MPI scalability and no GPU support. But it has the actual scheme we want to implement. Anyway, so first off, we reproduce exactly the solver. You cannot very well distinguish between the two curves, and that's normal. Basically, the two codes give exactly the same output, down to floating point errors. And now, if we can do meaningful performance comparison between the two. So, for example, we take a DGX, NVIDIA DGX workstation, and we run Phantom, that is an OpenMP code, on a EPIC 7742 64-core CPU. Here we'll get about 2 million particles treated per second with standard OpenMP. And now, if we are using adaptive CPP OpenMP backend with Shamrock, we'll get about the same performance. This is expected as we are dominated by the physical kernels, and that's where we spend the most time. So it's only logical that we get a similar performance to Phantom. Now, if we move to GPU, using, for example, Intel LLVM CUDA backend, we'll gain about a factor 6 compared to CPU execution, provided that our simulation is large enough. Also, I did a few weeks ago a small comparison across backends and implementations. So in general, for us, the performance depends a lot on the hardware, but not much on the implementation or even the given backend of the implementation. We get similar performance across the board, except for a few oddities like adaptive CPP, SMCP over ROCm LLVM. It's great on AMD. I don't know why. Anyway, we also had the opportunity to test the code on a multi-GPU cluster. So here you have the Adastra supercomputer, the largest one in France, that has 300 nodes. So basically the same node as on the Frontier supercomputer. So 8 logical GPUs per node, or 4 physical chips. But that's what we did scale on. So this is a weak scaling test. And here you can see the performance in number of particles treated per second as a function of the number of the GPU. And as you can see, we scale basically linearly here. And we get up to 65 billion particles in that simulation at a rate of 9 billion particles treated per second, which is about 7 seconds per iteration on 1,000 MI250X. Here, for reference, if we compare to Phantom, it's about a speed up of 5,000, as Phantom was not scaling well and had only 2 million particles per second. So now, if we divide that performance number by the number of GPU and by the performance on a single node, we get the parallel efficiency. And as you can see here, if you are taking a simulation that is large enough, you will get about 92% parallel efficiency on a weak scaling test. Now, we want to maybe run some actual simulations. And this is an example of such. Here you have what we call a circumbinary disk. So it's basically a disk of gas that orbit around a system of 2 stars. Here, the 2 stars are basically here and there, if I can point correctly, the 2 black dots. And as you can see here, you have some gas basically that will fall in the cavity and basically that will ultimately fall on the stars. To resolve that, you need quite a lot of resolution. So if we start at 10 million SPH particle, basically you get something that is very blurry in the center. You cannot resolve at all the physics that is there. Now, if we move to 100 million SPH particle, which is, for reference, the largest you could do with phantom, you will start to get some stuff in the middle, but the resolution is still not enough to get structures that are stable. Actually, one of the disks just goes away after some time because it's too dissipative. So if we are running this time on the Ad Astra supercomputer, we can do a simulation with instead 1 billion SPH particle on 8 nodes of the cluster here. And as you can see, this time we get actually resolved structures in those disks with what we call tidal features, as well as secondary instabilities that develop on the edge of the cavity. And basically, that's where we are at now. So using on-the-fly build trees with patch-based domain decomposition, and using SYCL to actually target all the GPUs, we achieve about 92% with scalability on uniform test and can use the code on actual production run now. Next will be for us to do actual exascale disk simulations, add way more optimizations, so typically related to performance and latency in general, add more physics because we are still a bit lacking in that domain since the code is fairly new, and add some load modeling. So in general, the code is already available. It's public on GitHub since about a month now. If you look up Shamrock code, you will be able to see it. And basically, that's where we are at. So thanks a lot for listening, and I'm happy to take your questions.
Thanks. One question about the implementation. So it's meant for using on MPI clusters with multiple nodes, but does it also work with multiple GPUs on a single node without MPI?
No, it's always, so maybe I did not mention it, but basically that picture tells the story very well. That's basically how we run the code. One rank is one GPU. It's just much simpler for MPI communications.
Okay, thanks.
Basically, communicating between two MPI ranks will be communicating between the two GPUs.
Yeah, I have a question in the context of OpenCL discussion, which Ben have talked, and also all the previous examples of successful OpenCL adoption. What prompted you to choose SYCL over OpenCL for your work?
So initially, I was actually using OpenCL, and I decided to migrate for many reasons. The main one being that basically it was too much of a maintenance burden to stick with OpenCL. The kernel were becoming way too large. We started to add quite a lot of logic to basically handle which kernel do we use at which time. And we figured at some point that just single source was the way to go. Also, initially we were using SYCL buffers, but really the combination of SYCL buffers was just great. For maintainability, we just add the kernels, everything is scheduled automatically, and it reduced the code size by quite a lot.
Thanks.
Thank you very much for the excellent talk. Yeah, someone has to be the first adopting SYCL for Astrophysics project, so great work here. My question is regarding the networking. How much does the network bandwidth become a bottleneck? It's so many, like 1,000 GPUs.
It's not. it's negligible. I mean, in our case, really, the network is not much of an issue. I mean, everything in the code is designed around weak scalability. So everyone is independent. There is no master rank or anything like that. And everyone shares the metadata, which means that basically everyone can compute which message it has to either receive or send. And everything, basically everyone processes their communication table in advance, and we just have to perform the communication. And thanks to direct GPU communication, everything is quite quick. Latency is okay. So it's very small compared to the physical kernel, actually.
So since you have a very capable machine with a very capable CPU and a very capable GPU, and you also did test some CPU results, I was just curious, would it be possible to mix CPU and GPU in your model, or do you basically have to stick to just doing everything on GPU, or do you see a benefit of mixing it?
So technically in the framework, we do support having multiple kind of queues. There is a compute queue and alternative queue, where basically I was initially doing the load balancing on the alternative queue, which was typically, for the case of adaptive CPP, I had one queue on CUDA and one queue on OpenMP. before. But the issue, I mean, for everything that I tried it with, it was just faster to run it on the GPU every time, even at the cost of additional communication. So at some point I figured, well, I just do everything on the GPU and that's it. And actually the data of the simulation is always in the GPU. It never goes back to the CPU. Unless you cannot do direct GPU communication and have to fall back to host communications. But that's the only edge case.
All right, thanks.
Sorry, this is a bit of a physics question, actually.
Ooh.
Do you consider any relativistic effects in your simulations, or is this?
We are in the process to consider them slowly. So first off, I mean, it's not included in that presentation, but do we have an example? Probably no. But typically, when you do cosmological simulation, yeah, no, I don't have any example. When you do a cosmological simulation, you may want to have typically like just the covariant comobile coordinates. This is very easy to implement in typically a good enough scheme. There is also a variant for SPH, so this could very well be implemented. It's just basically an external force or changing the conservative to primitive variable conversion, but that's basically it. So yes.
Hi, thanks for the talk. So you mentioned that you sort your particles along a Z-curve.
Yes.
Have you experimented with sorting, for example, along a Hilbert curve to improve locality?
So first off, we are using the Hilbert curve, but on the domain decomposition. So we have two kinds of curves in general. The choice of the Morton curve is not because it's a fractal curve. It's because there is some kind of duality between the actual number you get, I mean, the representation of the binary number you get as a Morton code and the radix tree that you want to build. There is a very clear hierarchy of levels already in the Morton code, and that's why we are using it for the radix tree. But if we were to change the tree algorithm, we could relax that, but since we are using this tree algorithm, it's kind of bound to Morton curves. But we can reorder the neighbor list if we want to improve locality.
Right, okay.